like to give those concepts in today's session too. So I'll just recap the major ones, the things that we spoke about yesterday. Uh, the main thing I think what I demonstrated was that an example with this game, we have this game called as a Galton board. You have a ball dropping from here. Whenever you have the ball dropping, the ball, when it meets uh, an obstacle, it can go either left or right, and it goes either way with equal probability. And then when it finally drops this way, results when you drop a huge number of balls, it results in a normal distribution because most of the balls tend to come in the middle. The point of that example was that if you want to calculate uh, the point of the example was that if instead of balls you have a photon, you have two photons, then if you want to calculate where exactly the photon will end up and whether they will interfere constructively or destructively, you would have, have to sorry, you would have to calculate all the possible paths and then figure out whether they interfere constructively or destructively. And to do that, the problem grows exponentially as the number of levels increases. So that was the point of the thing. As number of levels increases, I'll go to that slide where we have the. So yeah, as the number of levels increases, if you want to calculate or figure out whether two photons are interfering constructively or destructively, you would have to individually calculate all the possible paths. And as you can know, I mean, as you can figure out, it's going to grow exponentially. On the other hand, the quantum way of solving the same problem is that you actually build the experiment with, you take beam splitters, you have two sources of photons. When you actually build it, and you have when you actually build the system, and instead of manually on using a pen and paper, instead of calculating the possible number of paths, you just have these photon detectors over here. You actually run the experiment and you just count the number of photons that reach each of these detectors. When you actually build the system like this, you don't have two visible paths because the photon is actually traveling through, it doesn't, the photon doesn't take all the possible paths, but it takes some paths. And based on which paths it takes, when you repeat the experiment a number of times, you get the same information. So the point of all of this was that when you do it in the classical way, as the complexity grows, the time required to solve it grows exponentially. Whereas when you do it in the quantum way, or the way a quantum computer solves things, the time required to solve the problem only grows linearly. And this is where the speed up comes for a quantum computer. So yeah, that was the point I wanted to make. The black one is for the classical computer. As the complexity grows, the time required to solve the problem grows exponentially. Whereas for a quantum computer, the time required to solve the problem grows linearly. So once you have sufficient number of levels, the time required by the quantum computer is far less compared to the time required to solve the same problem by a classical computer. So another example that I wanted to that I showed was the example of the soap film. So let's say the problem we have is that you have a number of holes in this shaft here, and you want to cover all of them with the minimum amount of material, which is, say, a rubber sheet, as you can see in this example. So to figure this out, like, what is the minimum, what is the shape, or what is the minimum area of rubber sheet that is required to cover all these holes using, a single sheet of rubber. That's not a very easy problem to solve, but you can solve it, practically, or actually, build a physics system that solves the same problem. If you build, a loop of wire in the same shape and dip it into a soap, dip it into a solution of soap, then you form a film of soap. And as you know, the soap film minimizes its surface area because it wants to minimize the surface tension. So the shape that this film of soap takes is actually the solution to the problem that we wanted to solve. And in a way, this really illustrates the way quantum computing works. The soap film is not actually doing any computation. The film of soap is just going about doing its own business. It wants to minimize the surface area, it wants to minimize the energy. It's just that when we happen to give it a film of wire, a loop of wire that is the same shape as the problem we want to solve. So it's our good fortune that we get a solution very quickly. Whereas you can imagine if you wanted to compute the solution to this problem, it would have probably taken a long time. And another reason the other point I wanted to illustrate with this example is it shows you how limited a special solver these sort of computers are. So the point I want to make is a quantum computer is not a general purpose computer. It is very fast, but it is very fast only for a very specific range of problems. So for example, you can imagine, just looking at this example, this film of soap cannot calculate, in general purpose problem. Even if you give it a simple problem like 2 plus 2, it is not going to be able to solve that problem. But if you give it a complex problem like this that it is well suited for, it is going to do it ridiculously fast. So that's the other point I want to make. A quantum computer is not necessarily a general purpose computer. They are very fast, but they're very fast only for a specific class of problems. And most of these are, optimization problems. And I mean, it's very analogous to the way quantum computers work. In this case, you have a film of soap that is trying to minimize its surface area and minimize the surface tension. In a quantum computer, similarly, you usually have qubits, or it could be represented in any way. You might have electrons that are trying to minimize the energy that they have. So that's a point I wanted to make with this example. So I think when we work with quantum computers, it's very important to ask two questions. One is, which of our classical computational problems have a quantum aspect? And how can we efficiently map that problem onto a quantum system? Just like we were able to map, the the problem of covering holes with a rubber sheet onto a film of soap. We need to figure out how to map the problems that we have onto a quantum system. So yeah, with that, I came to this definition which said a quantum computer is a machine that performs calculations based on the laws of physics. The Galton board and even the film of soap, they are also in a way physics computers. They solve certain problems using the laws of physics. A quantum computer also solves certain problems using the laws of physics. In the case of a quantum computer, it's based on the laws of quantum mechanics, which is why we call it a quantum computer. So I just briefly explained, the comparison between quantum computing and classical computing. I think the most important point here is the power of quantum computing really comes up when you see, as we saw in the case of the Galton board, the the time required to solve a problem by a classical computer increases exponentially, whereas a quantum computer just increases linearly, and that's where the real speed up happens when you compare quantum computing to classical computing. So yeah, I had briefly mentioned qubits. I think we'll go into a little bit more detail into qubits today. But just like to recap again, a classical bit, you can have only 0 or 1. A classical bit that we use in classical computing can only take one of two values. It's either 0 or it's either 1. And we have many ways of representing a classical bit. We can use a current in a transistor. For example, if the transistor is on, you can say it's a bit 1. If the transistor is off, you can say it's bit 0. You can also use a magnetic domain, which is the way we store zeros and ones on these hard disks. So essentially, any two-state system or even a switch, when a switch is off, you can say it bit 0. When a switch is on, you can say it's bit 1. So any two-state system can be used as a classical bit. So a quantum bit or a qubit is again a two-level system. The only difference is that it's a two-level quantum system. And just like we have various implementations for a classical bit, you can have various implementations of a quantum bit. Typically, we use electrons or photons or traps to represent these qubits. And we'll take a look at these various methods in a little bit more detail today. So the other point I mentioned is uh, a classical bit can take only two values, 0 and 1. A quantum bit, on the other hand, can take on a combination of 0 and 1 values. It's very similar to the way you have vectors. So I'll draw the thing I had drawn earlier. So let's say you have a vector, uh, a 2D vector space like this. You have the x-axis over here, and then you have the y-axis over here. You can imagine in case of a classical bit, like, the classical vector is that if there's a vector that can only take x values, let's say it is only in the x direction or in the y direction, that's sort of like a classical bit. So let's say if it's x, then it is a value 0, or when it is y, it is value classical bit 1. So that's the way classical computing works, right? A bit can only be 0. So let's say when it's 0, it is over here. And when it is 1, it is over here. Now you can imagine that in case of a qubit, what happens is that it can take on any value in this entire 2D plane. So let's say it is over here. It's very similar to a vector, right? So let's say the qubit is over here and its value is q. So it has an x component over here and it has a y component over here. So you can represent it as, let's say the length of this is alpha, or the length of this y component is beta. So how would you represent this as a vector? You would say it's like, alpha. Sorry, my handwriting is quite bad. Let me try that. So in this case, this vector, you would write it as alpha, and then it has an x component. So let's say unit vector x cap plus beta, and then the y component of the vector. So this is how you would write it as a vector, right? So it's exactly the same for a qubit, except that in this case, instead of x, you would have 0, and instead of y, you would have 1. So that's the way you would represent the qubit uh, in q here. Another way of writing that, instead, if you don't want to write it so, such a long form, is you can just write it in the form of a matrix. You can, sorry, not this. You can write it as a matrix and just write its coefficients. You can just write alpha and beta. So I hope this is clear. It's very simple. It's just like a vector, right? It has two components, alpha and beta. Uh, so that's why I said quantum bit is a superposition or a linear combination of 0 and 1. Just like a vector is a linear combination of its x and y components. And just like a vector is a point in a 2D vector space, a qubit is also, essentially a point in a 2D vector space. The only difference is, I have drawn a 2D plane here, which has only real values, but in fact, actual qubits can have imaginary coefficients as well. But the point is the same, it's just a combination of 0 and 1. So when people usually say a qubit can take both 0 and 1 values, this is what it essentially means. It's a linear combination of 0 and 1. So, and another thing is, just like, for a classical bit, you have certain requirements to represent it. We have certain requirements to represent a classic qubit as well. Uh, very similar to the requirements for a classical bit. Let's say if you have a classical bit, so you would want the ability to set it to 0 or 1. Similarly, when you have a qubit, you would want the ability to initialize it to 0 or 1. In case of a classical bit, you would want to have the ability to, keep it at its value. If you write something into a pen drive, say, you would want it to remain there for a long time. Similarly, in case of a qubit, if you set it to a particular value, you would want it to remain there for as long as possible. In case of a classical bit, we would, I mean, it's not enough to just have zeros and ones. You want to do computations on them. And the way we do computations on classical bits is using logic gates. Similarly, when you have quantum bits, you want to be able to do computations on them and manipulate them. So the way you do them is again using quantum gates. Again, we will look at quantum gates in a little bit more detail in the coming slides. And then again, for a classical bit, you would want the ability to measure it. It's whenever we want the ability to read a bit and see whether it's 0 and 1. Similarly, for a quantum bit, you want the ability to measure it, and find out it's whether it's 0 or 1. And finally, it has to be scalable. As I mean, as well know, Moore's law in classical computing, the number of transistors on. Sorry, let me just drink some water. So yeah, as you're all familiar with Moore's law, the number of transistors on our chips have kept increasing over the years, and it's evident in the way our computers have become more and more powerful over the years. We are able to fit in more and more transistors on the same area. In the same way, when you have a quantum computer, when you have qubits, eventually in the future, we would want to scale it up. We would want to increase the number of qubits. So we would want a technology that is scalable. So yeah, these are things that we looked at yesterday. Uh, these are the various implementations of qubits that I had mentioned. We will look at each of these in a little bit more detail. Uh, Again, this is a very important point that I wanted to reiterate. That is, a quantum computer is not a general purpose computer. It provides a huge speed up, but only for very specific problems. Good examples of problems where quantum computers provide good speed up are, cryptography problems, optimization, protein folding, drug discovery. Again, optimization is, I keep mentioning this because it's a very broad range of problems. And again, the reason quantum computers work very well for optimization problems is because it is essentially an energy minimization problem. Again, it becomes very intuitive when you think about the soap film. The soap film, essentially what is it doing? All it's doing is it's reaching a state where its surface area is minimum, and its surface tension, or the energy associated with surface tension, is minimum. So similarly, when you have a quantum computer, all an electron is trying to do is reach its minimum energy state. So when you map a problem onto this physical system, essentially what it's doing is optimizing, the problem space that you have to reach an optimum solution where the energy is a minimum. That's an intuitive understanding of why quantum computers work very well for optimization problems. So a few challenges associated with quantum computing. Now, of course, like it's very similar to the development of the classical computer. Classical computer, we have reached a stage where we are very easily able to, do a lot of computations, easily able to manipulate, classical bits, compute them and all. But in case of quantum computers, we are at a very early stage. In fact, we are struggling to even make, a quantum computer with a few qubits. The qubits, as we will see in the coming slides, are very susceptible, very delicate. They are not like classical bits. I mean, the point is, if you compare classical computing and quantum computing has a long, long way to go. We are in the early stages, so there are a lot of challenges in the field. Some of these are, there are stringent requirements for the environment. And I think it's very intuitive. When you have an electron, it's very easy to imagine how easy it is to disturb a single electron. Any temperature fluctuations, and there is enough energy for the electron to, jump from one level to the other. So what is typically done is you reduce the energy and make sure that the electron is not, moving, having random fluctuations. And typically that is done by cryogenic cooling. you cool, typically these systems are cooled to, very close to absolute zero, a few millikelvin sort of temperatures. And this is done in these, big dilution fridges. And as you can see, as you can imagine, these systems are not going to be pocket friendly. I mean it in both ways. They are not going to be compact, and they're not going to be cheap. So, current technology, current quantum computing technology is definitely not pocket friendly. So, yeah, and I think yesterday we summarized with by saying that in a real sense, quantum computers do not compute at all, but they simply carry on according to the laws of physics. Again, if it becomes more intuitive when you think of the soap film. The soap film isn't really, computing or doing anything for us. It's going about doing its own business. It's just that we manage to map the problem that we have onto its system and use its laws of physics to solve a problem. And I think just like, the soap full only if we are able to map the problem that onto its, the loop of wire that we use. Similarly, quantum computing is going to be useful to us only if we have the ability to map the problem that we have onto the quantum system. So yeah, with that, I think, yeah, this is new material from today. So various ways you can implement a qubit. Now, I know this is a lot of information, but we will go into it one by one. Now, these are the various ways that I've already mentioned, and I'll go into, uh, a brief description of each, examples of who is using which technology for quantum qubits, and the various pros and cons of each of those. So, so again, like I said, quantum bit in a classical bit is the smallest unit of information that is used in traditional or classical computers. And in case of the classical bit, like I said earlier, you can make a bit out of anything that has two states. In one of the earliest examples, when punched cards were being used, a bit was just a hole. If there is a hole, you can say it's a zero. If there's no hole, it's a one. You have a CD, compact disc. In that case, a tiny dent on the metal surface is a zero or a one. So if there is a dent on the CD, it's a zero. If there is no dent, it's a one. And similarly, in case of hard disk, it's a magnetic domain. So if the magnet is polarized one way, it is a zero. If it's polarized the other way, it is a one. In case of a solid state disk, or a pen drive, essentially it's an electron charge. So if you have an electron over there, it is a zero, or if there's no electron over there, it's a one. Similarly, a qubit is also a two-state system. The only difference is that the qubit is a two-state quantum system. And there are certain properties that I already mentioned. I'll not go through it again, that we would like the two-state quantum system to have. So, so these are some of the qubit implementations. So again, these are just some of I'm sure you recognize some of these big names like Intel and, of course, Google and Microsoft and all. So currently, it's like there are various competing technologies to implement a qubit. There is no clear winner yet. Different people are approaching the problem in different ways. And as of now, no one really can predict the future. We can just wait for it and see who wins. But each of these technologies has their own advantages and disadvantages. So we'll just take a look at each of those. Now, briefly, there are these various ways to implement qubits. You can have superconducting qubits. You can have ion traps as a qubit. You can use photons as a qubit. You can use neutral atoms of a qubit, and you can also have, silicon and topological qubits. We look at each of them in a little bit of detail. Um, so I think superconducting qubits are qubits, because this is the technology that is, most popular right now. In fact, this is the technology that was, you must have heard the news of Google demonstrating quantum computers in their Google also uses superconducting qubits. So superconducting qubits has not won the race yet, but it is definitely leading the race currently. So as the name suggests, superconducting qubits essentially uses a superconducting current to to implement the qubit. As you know, a superconductor is a wire that offers no resistance to the flow of current. So in case of superconducting qubits, again, I'll not go into a lot of details, but I'll just give the brief overview of, just a brief summary of the way things work. So in case of a superconducting qubit, typically what you have is, you have a superconducting, let me write. So typically what you have is you have a slab of superconductor, then you have an insulator in between, that's I, and then you have another superconductor here. It's typically called, it's also called as the Josephson junction. So you have two superconductors separated by a narrow gap, which acts as an inductor. And when you have an inductor and a capacitor, as you know, you have a resonant circuit over here. So this resonant circuit is sort of used as a qubit, and that's the way superconducting qubits work. And as I said, it is sort of the leading technology right now, because several big names use superconducting qubits right now. The biggest names, in fact, IBM, Google, Intel, Rigetti, they're all trying to develop quantum computers using this technology or this way of implementing qubits. So what are the advantages of superconducting qubits? Are that the gate times are very fast. That is, the quantum gates that you implement using this technology are quite fast. And superconducting processes are actually very similar to semiconductor processes. So as you all know, the semiconductor silicon technology that we have right now, we have a lot of experience, we have a lot of infrastructure with that. So if we are able to use the same existing process to fabricate these superconducting qubits, that is a huge advantage, because we don't have to develop new technology for these things. Of course, there are some problems with it. The fast decoherence times. By decoherence, I mean they are very susceptible to environmental noise and can be, disturbed by environmental noise. So it needs to be kept very cold. Like I said, the temperatures are typically very close to absolute zero. In this case, the temperatures are usually, less than 100 millikelvin, or that's like, almost like less than 0.1, close to absolute zero. So as you can imagine, it's not going to be easy to do that. Another, probably the technology that is second in the race currently is ion trap qubits. So the way ion trap qubits work is, as the name suggests, is you have an ion that's a charged atom, and then as atom. So if you use an electric field, you can control the movement of the ion. So you have electric fields that hold the ion in place, and then the electron that is present in the outermost orbit of the ion is used. An electron, it can be a two-level quantum system. The electron can, you can give energy to an electron and move it to another level, energy and move to another level. So the outermost electron in the ion is used as a qubit. And the people using it as sort of like, IonQ and Honeywell are trying to develop technologies using ion trap qubits. The biggest advantage of ion trap qubits is the stability. They have long coherence times. They are not as, sensitive as superconducting qubits. They still need to be cooled, but not to the extent of superconducting qubits. The problem with this is that they are slower than superconducting qubits. Another problem is that it needs high vacuum. Now, the technology is not mature as silicon technology or superconducting qubits. So that is a problem. Another big problem is that scalability is a question. It's not, I mean, we are not sure how scalable this technology might be. And another thing is, as you can imagine, you need technologies from a wide range of domains. You need ions, and then this is held in place using lasers. So you need optics or photonics expertise. It needs a high vacuum, so you need vacuum technology. So you need technologies from can always get complicated. So that's another con of ion trap qubits. But interestingly, the first quantum logic gates that were demonstrated were done using this technology. Yeah, so another way of doing it is photonic qubits. As the name suggests, it essentially uses single particles of photons of lights, which are operating on silicon chip pathways. There are a couple of startups employing this technology. The biggest advantage of this technology is that it does not require extreme cooling. In fact, there is speculation that this is the technology that can work at room temperature. Another advantage is that it uses silicon, and like I mentioned in the case of superconducting qubits, silicon technology is very mature. We have a lot of experience with it. We have a lot of infrastructure and expertise with working with it. So whenever you can work with silicon, that is a big advantage for any technology, because you don't have to invest in new machines, or develop new processes. You have existing processes and you can use the existing ones. So that's a big advantage for photonic qubits. The problem is that's probably the biggest problem with photonic qubits. Yeah, this is neutral atoms. It's very similar to the ion trap, but as the name suggests, instead of using ions or charged atoms, we use neutral atoms instead of ionized atoms. And these atoms, you can't use an electric field to hold them in place. So we instead use laser tweezers to hold these atoms in place. These have sorry, similar advantages compared to the ion traps, that is long coherence times. But they have a unique feature compared to ion traps, that is the potential to build multi-dimensional arrays. But again, as in the case of ion traps, scaling is an issue. We are not sure whether the technology is scalable, and again, the technology is quite new and nascent. Uh, this is another interesting concept, using silicon for the implementing qubits. Essentially, what you can do is you have electron spins in silicon, right? So I guess you're familiar with the concept of electron spin. Uh, Using the spin of an electron, you can have two-level systems, whether the electron has spin up or spin down. These are the two states of the that are used for a qubit. So again, Intel is trying two technologies. So this is one of the technologies that Intel is trying, and there are some other people trying it. Uh, the pro for this is that if successful, this will allow for long coherence times compared to the superconducting approach. But of course, the con again is that whenever you deal with electrons, they're extremely susceptible to noise. So you need cooling there. Another way is topological qubits. Um, Again, not going into much of the details, but it uses quasi-particles like Majorana fermions. The biggest problem with this technology is that these Majorana fermions are they're predicted theoretically, but they have not been observed experimentally yet. A big name like Microsoft is currently pursuing it. The biggest pro with Majorana fermions is that they are very rugged. They are very uh, they are not susceptible to environmental noise. So you can have very high coherence times and high fidelities with it. The biggest problem is it's established that these particles exist in theory, but there's no practical evidence for their existence yet. There's a lot of work going on to find these fermions, but and currently there's no practical evidence for the existence of these particles. And another way to implement qubits is diamond vacancies. So as you know, diamond lattice is carbon atoms. So what is done here is you have you sort of like doping. You have a nitrogen atom in the diamond lattice, and when you have a vacancy in the nitrogen atom, you can add an electron to that trap system, and the energy of that electron can be controlled with light. So you shine a light there, it gains energy and goes to a higher state, and then it can also give out energy and go to a lower state. So that's another way we can use diamond vacancies to implement a qubit. The pro is that this can again operate at room temperature, but these are difficult to entangle, these particles. So that's a con for them. So overall, yeah, I know I showed this slide before, but just showing it again to summarize. Superconductor, like I said, there's no winner yet. We don't know which technology is going to win or dominate. Or it's also possible that you have more than one technology, and depending on the application, we will use one technology or the other. But currently, if there is a leader in the race, it is superconducting qubits. And the recent news of Google demonstrating quantum supremacy, that was done using superconducting qubit technology. And yeah, again, this is just a summary of the each of those technologies, their pros and cons. I'll not go through this whole table again, but this will be there in the slides for your reference in the future. Yeah, so before I go on, are there any questions so far? I think that pretty much covers the various ways to implement qubits. I detail because it's really difficult to go into the details of these technologies in such a short time. My goal was just to give you an idea of the various approaches that are possible to implement qubits, and just briefly mention what the pros and cons of each of these technologies is. But yeah, before I go to quantum gates, are there any questions so far on this, or okay, I guess if there are no questions, I will move on. So the next topic is quantum logic gates. Um, so like I said, just like you have classical logic gates, you have and or not gates, you have quantum logic gates as well. But there's a little difference in the way these logic gates work, and I'll go through it again, slowly and step by step. Um, so like I said, the difference between a classical bit and a quantum bit is that a classical bit can only take two values. That is, a classical bit can only be, let me write it here. A classical bit can only be either 0 or 1. Now, like I said earlier, with a quantum bit, it can take a linear superposition of values between 0 and 1. And just like in the case of a vector, a vector can be, it has an x component and a y component. A quantum bit also has, an x component and a y component. The difference is it's not x and y, it is 0 and 1. So let's say there's a qubit with an alpha and a beta component. That is, alpha is 0 and beta is 1. So all that means is that if I draw the 2D plane again, you have 0 over here. And you have 1 over here. Then if you draw a point, let's say the qubit is over here, then its x component or 0 component, this length is alpha, and this y component or this 1 component, the length is beta. And this is sort of the qubit. It's just like a vector in this 2D space. And like I said, instead of writing it like this, you can also write it as a matrix with just its x and y components. So it's just two elements in the matrix, it's alpha and beta. Now, in case of let's look at the simplest example of the NOT gate. So, in case of the classical bit, we know what the NOT gate does. If you have a 0, the classical NOT gate will give you a 1. If you have a 1 in classical gate, the NOT gate will give you a 0. Now, how does it work in case of a quantum bit? I guess a bit of it is intuitive, but still I will go through it. Let's say the quantum bit is just 0, then it's pretty straightforward, right? If in case of a qubit, if its value is 0, of course the output will be 1. And similarly, if the input is just 1 for a qubit, then again the quantum NOT gate output will be 1, will be 0. But what happens when you have a superposition of values like this, or alpha and beta? So in that case, all that happens is that these values switch places. So let's say the input to the NOT gate is this qubit with alpha and beta. The output of the NOT gate will again be another qubit. The only difference is the coefficients are interchanged. It's beta and alpha. And when you write it as a matrix like this, usually these operations can be represented as matrix multiplications. So I guess it's can you tell me what matrix you can multiply this alpha beta by to get this beta alpha? Yeah, the answer is right here. So it's like if you have the matrix alpha and beta, and you multiply it by what is also called as, sorry, let me write that again. I should write that first. So say you have the NOT operator like this, 0. And you multiply this by the qubit alpha beta. The result is the output of the NOT gate. So when you represent these qubits as matrix operations, the NOT gate is represented as this matrix. So again, I don't want you to get confused with the details. The essential point is, in case of the classical bit, the only thing the NOT gate does, it takes a 1 and makes it a 0. It takes a 1 and makes it a 0, or it takes a 0 and makes it a 1. In case of a quantum gate, it is slightly more involved, because it's not just 0 and 1, you have alpha and beta as the coefficients. And the only thing the quantum NOT gate does, it switches the coefficients. So if you have alpha and beta and you apply a NOT gate to that qubit, the output is beta and alpha. That's all I want to say. And as you know, if you apply in the classical bit, you apply the NOT gate twice, you get the same output. Similarly, it's exactly the same for the quantum logic gate. If you apply the same NOT gate twice, you get exactly the same output. And that's also shown in this matrix representation. If you multiply two NOT gate matrices together, you get the identity matrix. So, so yeah, I just took this because I was worried I wouldn't be able to write all this. But yeah, it's again the same thing. In case of a quantum NOT gate, you have, if the input is 0, the output will be 1. In case the output is 1, the input is 1, the output is 0, exactly the same for the classical bit. It gets a little different when you have, alpha and beta coefficients, but the only thing that the NOT gate does is switches the coefficients together. And its matrix representation is, like this, as we discussed. Now, again, I know there are various other gates like the Hadamard gate or the phase shift gate and all. Due to lack of time, I will not be able of this. But the point I want to make is, as you saw in the case of the NOT gate, all of these representation are represented in the form of matrices, or That's why I said linear algebra is quite important for quantum computing. A qubit, as I said, is very similar to a vector. A vector has x and y components. A qubit also has x and y components, so 0 and y components. So just like a vector can be represented as a matrix, a qubit can also be represented as a matrix. And the operations on vectors, as you know, they can be represented as multiplications of with various matrices. Similarly, when you operate a gate on a qubit, that can also be represented as matrix multiplication. That's exactly what we saw in the case of the NOT gate. When you apply a NOT gate, it's exactly the same as multiplying a matrix with the qubit. So that's the point I want to illustrate here. And I'll not go into the details of other gates, but they're very similar to the NOT gate example that we saw. It's essentially a multiplication of a 2 by 2 matrix with the coefficients of the qubit. That's all there is to it. So it's again, this is an example of a 2-input NOT gate. So NOT gate is a 2-input gate. The NOT gate had a single input, right? It had a single qubit as the input, and it gives a single qubit as the output. There are also 2-input gates. In this case, it's a it's a 2-input. You have 2 qubits on the input, and then again you have 2 outputs for this. So it's a 2-input gate. So this matrix multiplication is represented by a 4 by 4 matrix instead of a 2 by 2 matrix. Again, you can take a look at these in detail later. Go into just walk you through this due to lack of time, but the idea is exactly the same. It's change, but all gate operations are just matrix multiplications with the input qubit. That's what I want to illustrate here. So yeah, before I move on, I think this will be the final section of the presentation today. Are there any questions on the quantum logic gates before I move on to an example? Yeah, if there are no questions, I think. Sorry, is there a question? Okay, I guess no questions, so I will move on to the example. So this is essentially the final section of the presentation today, and I wanted to walk you through a more concrete example of quantum computing. I know we already went through 2 examples, but they were more like analogies to quantum computing. I thought this final example will give you a better understanding of exactly how quantum computing helps speed up computations. So the problem we are trying to solve here in this example is, let's say we have a travel agency. We have 2 taxis, and we have 3 passengers who want to travel. Let's travel from some place to some place. So you have 3. Sorry, you have 3 passengers: Alice, Becky, and Chris, and we have only 2 taxis, and we want to optimize their travel plans. But what are the constraints? The constraint is that Alice and Becky are friends. Alice and Chris are enemies, and Becky and Chris are enemies. So keeping these points in mind, the way we would want to arrange their travel plans is that you want to maximize the number of friend pairs who are sharing the same car, and you would want to minimize the number of enemy pairs that are sharing the same car. So obviously you have 3 people and 2 taxis, so there would be some sharing of cars. So you would want to make sure that the friends, that is Alice and Becky, are together in the same car, and that Chris is not sitting in the car with either of them because for some reason he is enemies with both of them. So how would you, I mean, I know this is a very trivial example, but it does illustrate how quantum computing helps to speed up such problems. So that's why I want to use this as an illustration. Now, how would we go about solving this, the natural way or the classical way of things? One way to do it would be you represent the taxis by, taxis by bits. You have 2 taxis. So let's say the first taxi is bit 0. and the second taxi is bit 1. And for each of these people, you have 3 bits. So let's say it's just a 3-bit system. Let's say you just have a 3-bit system for 3 people. And let's say the 3-bit number that you have is 001. So what this 001 represents is that Alice goes in taxi 0, Becky goes in taxi 0, and Chris goes in taxi 1. So similarly, to find all the possible combinations or the possible ways in which these 3 people can travel, all you have to do is list out all the possible 3-bit combinations that you have. And as you know, you have 8 combinations possible. Now, once you have all the possibilities there, it's very straightforward to calculate the score for this. Like I said, the goal of this is to optimize. The optimization goal here is that we would like to maximize the number of friend pairs that share the same car and minimize the number of enemy pairs that share the same car. So let's say the score of each configuration is, whenever you have a friend pair, you add 1 point, and whenever you have an enemy pair sharing the car, you subtract a point. So for example, in the first case where you have all 3 of them sitting in the same taxi, how many pairs do we have? So, if you remember, Alice and Becky are friends, so you add 1 point here. Becky and Chris are not friends, so you subtract 1. And then again, Alice and Chris are not friends, so you subtract 1 more. So you have 1 minus 2, which is minus 1. You get a score of minus 1. Similarly, in the second case, you have Chris traveling in in taxi 1, and Alice and Becky are traveling in in the first taxi. So again, the number of friend pairs that you have in the first taxi is 1. So you have a score of 1, and you don't have any enemy pairs traveling in the same car. So there's nothing to subtract, and the score is 1, and so on. So if you do this for all these combinations, you see that the best solutions are these 2. That is, either Alice and Becky travel in taxi 0 and Chris travels in the other car, or Alice and Becky travel in the first taxi and Chris travels in the other taxi. So when you want to solve such a problem in the classical way, the way you would do it is list out all these possibilities and calculate the score for each of them, which is actually the way a classical computer would solve these problems. It does it one by one. So it finds, it lists all these combinations, calculates the score for each of these one by one. And then, as you can imagine, how it grows, this is a simple example. You have 3 people, there are 8 combinations. If you have 4 people, there are 16 combinations. You have 5 people, there are 32 combinations, and so on. So you can very clearly see computer solves these problems. The computation time will increase exponentially with the number of people that you're trying to solve for. So if the same problem you're trying to solve using a quantum computer, again, it's a little difficult to intuitively explain these things, but I'll try my best. The way a quantum computer does it is, instead of, the main difference is, like I said, a quantum bit can take on a linear combination of values 0 and 1. So when you have A, B, and C, or 3 qubits for a quantum computer, it doesn't really it doesn't really take on 0 and 1. It takes a linear combination of values of 0 and 1, which is why the 3 bits here have been written as 0 and 1 on top of each other. Now, when you mean 0 and 1 like this, essentially it means that if there's a 50% chance that the bit is 0, and there's a 50% chance that the bit is 1. Similarly, when you have a combination of 2 bits like this, there's a 25% chance that these bits are each of these values. So when a quantum computer solves this problem, the way it would do it is, again, it's a little difficult to intuitively explain the way it does, because it's a little hard to understand the way it does. But if you go back to the example, if you try to remember the example of the photons, When we built the photon system using the beam splitter, you did not have to calculate each of the paths individually, right? The photon just travels on its path, and you directly have the detector which tells you the number of uh, which tells you whether the photon has constructively or destructively interfered. So if you recollect the photon example that we had, or the beam splitter example that we had, the photon doesn't, you don't have to go through each of those individual paths. You just have to run the experiment and you get the detector values. So similarly, when a quantum computer tries to solve these values, it doesn't have to each of these steps one by one. Or there's something like an operation that is done, just like in the case of the beam splitter example. All you have to do is, turn on the photon source and the photon travels. Similarly, in the case of a quantum computer, all you have to do is perform an operation on it, if I can call it that. You perform an operation, and then the computer just settles on the values that provide the maximum score. So in that case, it would either settle to this value or this value, since there are two maximum scores possible. So again, like I said, it's a little hard to imagine these things, but it will be easier if you again imagine the soap film example. The soap film, you don't really do anything. All you do is dip the wire of, or the loop of wire into a soap film. And then when you take it out, the soap automatically settles into a position where it minimizes the surface tension and minimizes the area. Similarly, in this case, you don't really have to do it individually. All you have to do is run the operation, and the bits automatically settle down into the value that provides the maximum score. So just like the soap film settles down to its minimum energy state, in this case the bits also sort of, if I can, I'm just trying to explain it intuitively, but the bits sort of settle down to a value where the score is maximized. So again, the speed up is evident here, because when you have, let's say you have 3 bits or 4 bits or 5 bits, the increase in computation time here is just linear as compared to the classical bit where the increase was exponential. So again, I know so it's a little hard to intuitively imagine the way this does. That's why I started with the examples of the soap film and the beam splitter example, because they provide a good explanation for the way these things compute in parallel or settle down to the minimum energy state. But I hope I managed to at least give an idea of where this speed up comes from, or what people mean when they say it computes things in parallel, or when they say it's both 0 and 1 at the same time. This is what they mean. You don't have to go through these values one by one. When you run the operation, the bits settle into these values themselves, because it's like settling into a minimum energy state for those qubits. So I think that's pretty much it. Before I go to the summary, are there any questions about the example? I hope I managed to, give an idea of the way the quantum computer computes. And any questions so far before I move on to the summary? Yeah, I guess if there are no questions, I'll go to the summary. Uh, So again, in summary, I'd like to say that a quantum computer is a machine that performs calculations based on the laws of physics or the laws of quantum mechanics. And that's again, I go back to the example of the soap film and the beam splitter example. They're not really computers. They're just physics experiments that are set up. They just go about doing their job and obeying the laws of physics, and they happen to solve some problems on the way. Similarly, a quantum computer essentially is just going about obeying the laws of quantum mechanics, and they happen to solve the problems that we want to solve. Another point I want to sort of, these are the key points that I'd like you to, remember from these two sessions. A quantum computer is not a general purpose computer. As you can see, these provide a lot of speed up, but they provide a speed up only for a specific class of problems. So the quantum computers are specific purpose computers and not general purpose computers. Then a computer provides an exponential speed up, but only in for specific classes of problems. A broad range of these problems are optimization problems, because many times most of these operations are just electrons settling down to their minimum energy state. So these map very well to optimization problems. And sorry, like we saw, there are various implementations of qubits. The sorry, the winner is yet to be decided, but the leader of the race is currently superconducting qubits. And finally, like I said, this is not a problem that we face in classical computing, but in quantum computing, we need the ability to efficiently map the problem onto the quantum system. So yeah, I just want to, like, I know 3 hours is quite a short time to give a good introduction to quantum computing, but my goal was to give you, an intuitive understanding or intuitive feel of the field, and just a glimpse of the things that quantum computers can do. If you want to read further, I think this is sort of a standard, like one of the gold standard books, Quantum Computation and Quantum Information by Nielsen and Chuang. This is a good book to start with, if you want to explore more of quantum computing. This is typically, a standard textbook also used for quantum computing courses. I mentioned the second one, Quantum Computing for Everyone, because it again explains things in a very simple way. It's accessible to anyone who, it doesn't assume a background on quantum mechanics or linear algebra. It's accessible to anyone with a background in high school mathematics. So that's why I put this here, in case you're looking for a more, general introduction to the field. This is a good one. And of course, I've given my email ID here. Even if you have any questions in the future, or you want to discuss something, I'm more than happy to do it. Please do write to me. I'm more than happy to interact and discuss any ideas that you may have. And yeah, I think that's the end of the session here. So yeah, any questions?
Sir, good morning, sir. I have one doubt, sir.
Yeah.
Sir, we are all speaking in terms of quantum physics and quantum, right, sir? Sir, I think what will be the speed of computations when we process on the system for a particular task? I mean, quantum physics or quantum means it's almost speed is almost equal to light of the speed now, sir.
Correct. Like, I mean, it's difficult to, I mean, just to give an example, for example, some of these cryptography problems, like if you say, if you want to, solve some of these cryptography or encryptions,
Yes, sir.
classical computers would take, I mean, it's said they take like, millions of years or something like that. But a quantum
Okay.
computer, it is said, it's not been done yet, but it is said that it's going to take a few minutes. But it's very difficult to give an answer to that question, because we haven't reached that stage yet. There's just been Google's the only real demonstration we have had is Google's demonstration of quantum supremacy, which again, it takes, I think, the Google's computer took a few minutes to solve that problem, whereas it is said the actual computer would take, several years to solve that problem. So I'm not able to, there's no practical demonstration of that, but these are the theoretical
I got
predictions that this is how fast it's going to be.
with your explanation, I got some ideas, sir. I mean, I got some answer. I mean, work is going on. So once it is proved, then we will say practical, right?
Correct. And I think the other thing I'd like to point out is it's for very specific classes of problems. Like even for example, the Google problem, right? It's only for that specific problem that it provides that huge speed up. If you give it some other, general purpose problem, it's not going to be fast. In fact, a classical computer might be faster.
Okay. Right, sir. Thank you, sir.
Yeah, thank you. Yeah, any other questions? Yeah, if there are no questions, I think yeah, I'd like to thank all of you for for the patience and listening to me for 3 hours. It's been a pleasure. Thank you for having me here, and I hope I managed to convey some useful information. And like I said, even if you have some questions in the future, just write to me, and I'd be more than happy to discuss and discuss further over email. Thank you. Yeah, thank you, thank you.
Thank you, sir. By this, we will end this session, sir. Thank you for your presence, and 3 hours we have more informative session by you. You have got knowledge on the topics. Thank you, sir. Thank you for your honorable presence in our STTP.
Yeah, thank you for having me here. Thank you.
Yeah, dear participants, again we will meet at 11:30 a.m. for session 2. Have break and come back at 11:30. I have shared the feedback link in chat box and also in the WhatsApp group. Please fill it out.